Hey rock buddies, it's Papa. Hope you're having a great day today. The weather's getting cooler. I know you guys like that too. Today we are going to talk about how you date rocks. That's not what it sounds like, of course. How they tell how old a rock is. We're going to talk about the law of superposition, where layers on top of layers. We're going to talk about fossils and index fossils, and we're going to talk about the super index fossil, which is conodonts. We're going to talk about radioactive dating, called radiometric dating, and we're going to talk about the coolest, newest method of radiometric dating, called the using zircons to date rocks. So stay tuned. If you like this video and it's helpful, please subscribe. And thank you so much to each and every one of you guys who has subscribed to my channel. I appreciate it. It helped so much. So here we go. Dating rocks. First, let's start off with sedimentary rocks. How to date sedimentary rocks. By sedimentary rocks, I mean rocks like conglomerate, sandstone, shale, and limestone. When we're talking about dating sedimentary rocks, we should keep in mind first the law of superposition. That just means that if you have a bunch of rock layers, one on top of the other, the ones at the very top are the youngest and the ones at the very bottom are the oldest. We should also keep in mind the idea of relative dating, which means if you have a bunch of rock layers, you know the younger ones are on top and the older ones on the bottom, but you don't know exactly what their age is, so it's relative to each other. Let's take a look at some pictures that'll help clarify these ideas. Here's a really pretty group of rocks from the Pennsylvanian time period in nice horizontal layers, one on top of the other. At the top you have a light colored sandstone, below that is a dark coaly shale, and below that are a thin layer of sandstone and a thicker layer of sandstone. The law of superposition just tells us that since the light colored sandstone on top is on top, it's younger than the dark coaly shale, and that the dark coaly shale is younger than the two sandstone layers below it. And even though we may not know the exact age in millions of years of these sedimentary layers, we do know their ages relative to each other, and that, my rock buds, is relative dating. Alrighty then, it's test time. You all know where this is. The Grand Canyon, right? You see the light colored layers on top and the red colored layers underneath. Which layers are the youngest? You are exactly right. The light layers, which are the Coconino sandstone and the Kaibab limestone on top, are the younger layers than the red layers below. Good going. Okay, rock buds, now let us talk about how to use fossils to date rocks. And here again, we're talking relative dating. But what is a fossil? Most people know what fossils are, but just in case, have a look at this definition of fossil and see what you think. And here come some pictures of fossils for your viewing pleasure. Geologists use fossils to date sedimentary rocks by focusing in on index fossils. Index fossils are fossils that mark a specific time period. In order to be a good index fossil, a fossil must be widespread geographically, it must be abundant in the rock layers, and it must have a short existence. In other words, go extinct pretty quick. Here's an example to kind of give you an idea of what an index fossil is. This little beauty of a fossil is called Finistella, and I collected it near Russell Springs, Kentucky. Let's assume that this Finistella is a really good index fossil. Let's say I went up to the area around Columbus, Ohio, and I found these same Finistella fossils. That's 400 miles away from Russell Springs, Kentucky. What does this tell me? Well, it tells me that in both places I'm dealing with the same period of time and the same rock layer. I know that these Finistella creatures were thriving during the Mississippian time period, between about 350 million years ago and 330 million years ago. But Papa, I thought you said this was relative dating. How come they know that Finistella existed during the Mississippian time and they know when Mississippian time was? Good question. In the beginning, a couple of hundred years ago when they first started doing this kind of thing, they didn't know. They just know that if you found Finistella in two different places and it was a good index fossil, then those rock layers in the two different places were about the same age. But over time, and geologists have amassed a bunch of data, and now they're able to tell that sort of thing. The march of science. Hey guys, here's a list of some of the most important index fossils that I know about. There are many, many index fossils, but I just thought you might want to see a few. Guys, now I want to tell you about one of the very most useful index fossil around. That is conodonts. Nice sound effect there, Thunder. This is what conodonts look like. Don't they look kind of like a bunch of teeth or little jaws with teeth in them? They're very small. Largest only get to about 2/10 of an inch long. They call these teeth-like structures conodonts, and they also call the critters that these teeth-like structures came from conodonts. Here's what they look like. Eel-like creatures that range from about a 1/2 inch long up to 15 inches long. It's raining like crazy here, rock buddies. We're filling up our drinking and washing water barrels. So why are conodonts such great index fossils? Let's have a look. So why are conodonts such great index fossils? Well, first of all, they meet all three index fossil criteria. They're widespread geographically, they're very abundant, and the different kinds of conodonts have very short existences. Conodonts are very durable, but the coolest thing about them is that their color changes with temperature and pressure and time. That means that you can look at a conodont and tell what kind of temperature pressure regime it was under, and so how deep it was buried in the earth, and that will tell you the processes that occurred. You can't do this in any other way with sedimentary rocks that I know of. Now let's talk about how geologists date igneous and metamorphic rocks. Examples of igneous rocks are granite, diorite, diabase, and gabbro. Examples of metamorphic rocks are granite gneiss, biotite hornblende gneiss, and metagabbro. These igneous and metamorphic rocks we've just looked at can all be dated using radioactive dating techniques, also called radiometric dating. Let's find out what that's all about. Almost all igneous and metamorphic rocks contain radioactive elements. A radioactive element is an element that naturally loses particles over time and is eventually changed into another element called a daughter element. And here are some examples of radioactive elements that you are very likely familiar with. You see, rock buds, since these radioactive elements decay at a known rate, scientists are able to compare the amount of the mother element with the amount of the daughter element being the element that the mother element morphs into over time. And they can tell how long it has taken to do that, and that gives us a date for the rock that contains these elements. Here are some of the most common radiometric dating techniques. Carbon-14 to carbon-12 technique is used only for organic matter. So let's look at the potassium-argon technique. When an igneous rock is formed, it has a certain amount of potassium, radioactive potassium in it. Over time, that potassium degenerates into argon, its daughter element, and scientists, by measuring the ratio between the potassium and the argon, can tell fairly accurately how long that's taken and thus age the rock. Hey rock buds, I know this can get a little confusing with the radiometric dating, but the main thing to remember is you can use radiometric dating to date igneous and metamorphic rocks, but you gotta be careful with the metamorphic rocks, because when rocks are metamorphosed, they get heated up and parts of them can remelt, and new radioactive elements can be formed. So the age that you get might just be the age of metamorphism, not the original age of the igneous rock before it was metamorphosed. Usually when scientists look at metamorphic rocks, they come up with two ages, generally speaking. And the oldest age is the age of formation of the igneous rock, and then the second or younger age is usually the age at which metamorphism occurred, and that tells them a whole lot about what was going on in the world at that time. Rock ladies and rock gentlemen, this is a mineral called zircon, zirconium silicate, and it is extremely useful to geologists for dating igneous and metamorphic rocks. I'll tell you why. Zircon is so useful to us because it's common in granite rock. The uranium-lead dating technique works great with zircon. And zircon is not usually melted during metamorphism, so it's easy to tell the ultimate age of the rock. And perhaps most importantly, zircon crystals have this kind of concentric ring kind of structure when you slice them very thin that tells us a lot about the entire history of the rock. First, they slice off very thin sections of the zircon about as thick as a human hair, and then they do what they call microanalysis, which involves all kind of interesting tests that I don't know much about. But one cool thing about it is that if they have a metamorphic rock, they can even tell if the original rock was a sedimentary rock instead of an igneous rock. Pretty cool, don't you think? Okay, rock buds, that's rock dating for you. I hope you enjoyed it and it was useful to you. And thanks for watching. And this is Papa saying happy rock hunting to all my rock buddies. Papa out.